Zoom? No, I'm asking to the students on the Zoom. Yes?
Yes, it's okay.
Yes.
I can see it. Okay, good. Okay, so good afternoon, good evening, everyone. So my name is Patrick Sebin. I think you are all from the first year. Second year. Okay, good. So, okay, the purpose of this presentation is to give you a brief overview of what we are doing in my group here in Bar-Ilan. So I'm Patrick Sebin from the physics department. I'm located in the Resnik building, if you know it, front of the nano building. So if you are very welcome to come and visit. This will be short, so don't hesitate to come and visit us, visit the group. So we are on the first floor of Resnik building. Okay, we are almost alone there. So it's a room 105 for my office. What is it? Beginning.
We can't hear you.
Let's see here. Is it better now, or it's a problem of connection? I have 5 messages. Can. Okay, good. Better with that. Yes. Okay, so let's start from where I come from. So from France, and I started in Nice, south of France. Can you see my mouse? No, there is a mouse here. So maybe this one. Yes, but I don't see it myself, so I have to go like that. So Nice is the south of France here. And that's where I did my PhD, and I started as a researcher at the CNRS, which is the research foundation in France. In France, you can do only research, no teaching. Okay, so that's very nice if you want really to focus on research. So after that, I did my postdoc in New York with Professor Azigenak at the Queen's College. And I went there several times for collaboration with him. And after that, I moved to Paris, and I became the director of research of the CNRS at an institute which is called the Langevin Institute. And just a word about it, it's very interesting that something that does not exist in Israel is that this is an institute where everyone working around the same thematics, around the same topics are gathered together, are working together there. So people working on waves, all type of waves, optics, acoustics, microwave, trying to understand what happened to these waves when they are multiply scattered in various environments, going from imaging to fundamental physics. But everyone collaborate together in this institute, and that's a very powerful institute actually in France. Here we cannot afford that. We cannot afford to have many researchers working on the same topic. So that's the drawback. So there, that's my team before I left like 7 years ago to move to Israel, where I got the opportunity to have a position here as an associate professor. So I did my Aliyah with all the family 7 years ago. And I built this group called Mesoscopic Optics and Acoustics, including postdocs, PhD, student, master student, also undergraduate students, and a lab manager, Leonid, who is taking care of the lab. In terms of teaching, I'm teaching usually the course on modern optics and laser. I'm teaching also the quantum optics labs for the students who want to practice, to learn what is a lab and to be able to join an optics lab. That's a very, very nice lab to be trained there. And there is an advanced course on light scattering in other media, except that this year I am on sabbatical on Shabbaton, so I'm not teaching, so you don't see me in class, except today. So just to give a rapid description. So essentially the main topic I'm interested in is multiple scattering and localization of waves, classical waves. I will talk about different applications, for instance, imaging through opaque media. If you want to do medical imaging through the tissues of your bodies, you need to have some information out of it. So that's the main application of this domain. But there are a lot of fundamental physics that I will try to explain to you rapidly today. And we have three labs. We have the optics lab, based on studying random lasers. I will show you actually what are random lasers. There is an acoustic lab where we study elastic metamaterials. I will define what do we mean by metamaterials. And a microwave lab. So microwave is also electromagnetic waves like in optics, except that they are macroscopic. The wavelength is typically a centimeter, okay? So we can model complex media at a scale which is a human scale, okay? So we can replay with the object, and we can really explore the physics of disordered system and multiple scattering of waves. So I don't go into the details. Collaboration, that's not very interesting for you, except that we collaborate a lot with a group from France, from the United States, from Germany. And I think that's it. Okay, so what I want to go over today with you is to talk a little bit about light scattering in random media, what I mean by that, and what are the concepts involved. I will give you some example here in the second part here about control of light in scattering media by gain and loss. Typically, we want to introduce gain in a disordered system and see if we can get lasing in such a system. And the third part, I will talk about metamaterials. So we are going to talk about structure media, okay, and how waves propagate in those media, and how we can actually design property which you would not find in nature. Okay, so we want actually to innovate and to create things that you don't find naturally in nature. Okay, so let me start with light scattering in random media with the first question for you. What makes light visible? Okay, if you don't have the source in front of you, if you don't have the sun, okay, you don't see light unless
it bounces off something.
It bounces off something, or it scatters on something. So here is the example of a cloud, okay, a white cloud. Why? Because the light coming from the sun is multiply scattered by these objects. So we see actually the reflection on the particles that form the cloud, okay? Second question for you on the Zoom also, if you want to answer. So here you have two types of system. One is a glass of water. The other one is a glass of milk, okay? And my question is why the glass of water is transparent and the glass of milk is white. What makes the difference between these two, okay? Both are made of particles, molecules, okay? One seems to scatter light The other one seems to be completely transparent to light. Okay. So what is your?
I think the reason for that some of the molecules in the milk absorb some of the light that comes to them and send back only a few others. That our mind translates as white. Maybe in this glass, all the waves go through. So we don't see a specific color. We only see what.
But my question, what do you mean when you say it goes through? Why it doesn't go through the milk as well?
Because the milk has some other materials that absorb some of the.
You know that if the light is absorbed, you don't see it.
Yeah, so they.
Absorption means black. Okay, something which is black absorbed completely.
It has to do with the scattering. When light is absorbed, it's usually re-emitted outwards, but it's at an angle of this. And light, it creates closer to be straight. So it looks like it's going straight through, but it really gets absorbed and then emitted.
You mean for the water, the glass of water?
Through the glass of water. With milk, the particles, it's scattered, it's random. It's more random. So
But why? I mean,
well, then it has to do with the actual properties of the material. With the scattering has to do with.
So what do you think? What kind of properties? Because light also is made. The water is also made of particles. Okay. So I expect the particles of the light of the water to scatter light too. Why not?
Maybe milk is more dense than butter.
Dense? You say more dense?
More dense.
The milk is more dense, so it's scatter light. If you take a piece of glass, okay, the glass is even denser than the water or the milk, and it is still transparent.
So maybe the structure of the individual molecules.
Yeah. So what do you expect the difference coming from?
There's nothing in there.
Okay. On the Zoom, any idea? Any suggestion? Any?
I haven't reached this part.
Maybe the energy levels.
Sorry?
Maybe the energy levels.
The energy levels?
Of the atoms, like if it's excited or not, and I mean the kind of if an atom has an electron attached to it, or it doesn't have all the electrons and stuff like that. I'm not entirely sure.
But here you go into a very complicated explanation. So interaction between light and matter. Actually, here the answer is much more simple. It's simply related. You have to compare scales. Okay, you have the scale of the light itself. Okay, what is its scale? It's given by the wavelength of the light. Okay, which is typically a micron. Okay, or less than a micron. Okay, and you have to compare that to the particles that form the material. Okay, so water is made of molecules of H2O. Okay, which are extremely small. Okay, we are talking about 100 of angstrom maybe. Okay, while in the milk, the particles are made of droplets of fat. Okay, and those droplets are quite big compared to the water molecules. Okay, and actually they are big enough to be comparable to the wavelength of the light. Okay, and that's what counts here, is that to have an interaction between the wave and the medium itself, there must be a relation. The scales should be comparable. Okay, and that's what happened in the milk. It's made of these droplets, which are typically micron size. Okay, and so the light see, if we can say like that, the light can see actually those droplets, and it is scattered by the droplets. So it's very important in this domain to compare the various scales involved in the system. So you have the scale given by the light or by the wave, which is the wavelength. Okay, so this is a picture representation of the wavelength, the oscillation of a field. Okay, and typically the wavelength is the distance between two maxima of this oscillation. And you have the size of the scatterers. Okay, so you can have big scatterers or very small scatterers. and the light will be sensitive, will interact with the medium if they have the same size, okay? This is a very rough description, but that gives you an idea, okay? So that's one aspect. There is another aspect that I will not detail, but which is very important too, is the dimensionality of the system, okay? You can imagine, for instance, that in one dimension, if you look here at an optical fiber, okay, if it's very narrow and it is a single mode fiber, then if there are obstacles, if there are scatterers inside the fiber, they will scatter light a lot of time, okay, because you have only one direction to go through, okay. While in 2D or even in 3D, the light can always go around and avoid the scatterers, okay. So that's a parameter which is very important in the physics that I'm going to describe, is the role of the dimension of the system that we consider, okay. I talked about light, but this is true for all type of waves, okay? So from electromagnetic waves to acoustic waves, matter waves, like waves water waves, for instance, electronic waves. This is a very general problem, how waves interact with different type of media. So to illustrate that a little bit deeper, I'm going to use this beautiful picture. Okay, so you recognize here, it's a long time we didn't travel, but you recognize the Eiffel Tower, okay, in Paris. And what I like in this picture is that there is a cloud, okay, and you see that the cloud has a density that increases with the altitude, okay, with the height, okay. So at low altitude, there is almost no fog, no scattering, and as you go up, you see more and more. The cloud is more and more dense. So if you look here at up to the first floor of the Eiffel Tower, okay, you see that there is no scattering, which means what? It means that the source of the light, which are the light bulbs on the Eiffel Tower, is directly seen. Okay, this is called a ballistic regime, where light goes to your eye directly, okay, without any scattering. When you go up to the second floor, you are in a regime which is called weak scattering, okay. Why? Because you still see the source, the origin of light, okay, but you see around that there is a kind of halo of light, okay. Why? Because the light not only goes directly to your eye, but it is also scattered once on some particles. So here the particles are droplets of water. That's what makes a cloud. So the light is scattered once on some droplet and goes back into your eye, okay. So you see this halo of light around the Eiffel Tower. If you go one floor more up, okay, sorry, wrong direction. So here, when you want to be on the third floor, actually you don't see the Eiffel Tower anymore, okay. You see diffuse light, okay, and you are in a regime which is called a regime of strong scattering or multiple scattering, okay. This is also what happens when you put a laser light through your skin. You can see the light, but the light is completely scattered. You don't see actually the details inside your body, okay. You cannot image directly your body just by lighting with the laser, okay. So that's this regime here where you are in the diffusive regime. Here actually we use some approach that is very robust and very useful, which is called diffusion approximation, and that's enough actually to describe this regime. So my question is, what happened now if we go one floor more than that, okay, in a regime where we have a very, very strong scattering up there, okay. Let's imagine that the cloud is so strong, okay, that somehow the light is almost trapped up there, okay.
You barely see anything.
Yeah, in principle, you don't expect to see anything. So that's the regime that we are investigating, which is a regime of very strong scattering. And this is a regime which is called the regime of Anderson localization. And that's what I'm going to to illustrate with a simulation. Okay, so let's try to model this problem here in a simple type of simulation that will give you a good idea actually of what's going on. So the model here is a two-dimensional system made of these small particles. Okay, so those small cylinders. Okay, they have an index of refraction which is larger than 1, in contrast to the background, the white background, which has an index of refraction of 1. Okay, so typically we can vary the index of refraction of these particles here from a small value 1.05 to 3, very high value. So from very low index contrast to very high index contrast. Okay, you can also vary the density. As you mentioned, the density can be also very important. And the size of the scatterers is very important also because it has to be close to the wavelength that we are exciting inside the system. So this model using Maxwell equation, this is a typical system of dimension 5 by 0.5 microns, and we inject light at the center of the system. Okay, and I will show you two examples, one with a low scattering contrast and another one with a high scattering contrast. So the first one is this one. It will be in the diffusive regime. So you see that we compare 1.5 compared to 1 for the matrix around. So let's see if it works. Okay, it starts by itself. So you see the light starts from the beginning, from the center of the system. There is a wavefront that spread like water waves on a pond. Okay. But you see also that there is a lot of light coming back. I can play it again. So you see that the light propagates like nice circular waveform, but there is a lot of light which is back scattered to the center of the system. Okay, so this is typical of multiple scattering, back scattering light in this regime. So that will be the regime of diffusion, third floor of the Eiffel Tower. Okay, if we go a little bit higher, now you are in the regime of very strong scattering. I really exaggerate the contrast here with 3 bit compared to 1. And look at what happened in that case. If it starts. Do I start it here? Okay. So we start from the center. The wave tries to expand, but actually it is trapped. You see that most of the energy comes back to the center of the system. Okay. So although there is space between the scatterer, to escape, but here what happens is that the light is completely trapped inside the disordered system. Why? This is a complex phenomenon due to interferences. You know that light, a characteristic of light is that it can interfere, okay, constructively or destructively. And what happens here is that there is a destructive interference forward, and there is a constructive interference backward, okay? And that's a result in this localization of light, this trapping of light inside the system. Okay, so now if you ask the question, I'm looking at this Eiffel Tower on the top, what would I expect? Okay, so this light cannot escape actually from the cloud. So what you would expect is a completely black picture like that, okay? Compared to the diffusive case, you would expect something black like that, okay? If you look at the spectrum in transmission of the system, okay, what you discover is that most of the time, indeed, there is no light. Transmission is 0. But for some particular values of the frequency, you can see sharp peaks. That means that the light can transmit through the system, okay, for these particular frequency values, which correspond to modes. Okay, those modes are modes that are trapped inside the system and that can tunnel actually the light, the energy through the system. So that's a typical example of a localized mode inside the system. So if I have light coming from the top here, it will couple almost evanescently to this mode that will be excited, that will actually store energy, and we release the energy on the other side of the system. And that's why you see these very sharp peaks in the system. And we are going to take advantage actually of this localized state, this localized mode inside the system to explore interesting things that I will show to you after that. So you understand that actually you can tune this degree of localization by changing the contrast, the index contrast between the scatterers and the matrix. So you can go from very strongly scattering media here, where you have a high index contrast, to modes which are more extended inside the system, to fully extended. That's the diffusive. That would be the diffusive regime that we mentioned. Okay, so you go from the 3rd floor to the 4th floor, the Eiffel Tower this way. Okay, so you see the nature of the eigenmode of the system is completely different depending on the degree of scattering inside the system. And that's a very interesting property. I just wrote here that the transport in random media is completely driven, completely controlled by the nature of the mode inside the system. And that was actually a discovery made by Phil Anderson in the 50s. He got the Nobel Prize for that in the 70s, okay? And his seminal paper was titled Absence of Diffusion in Certain Random Lattices, okay? And actually he asked, he developed his theory in the context of electrons, okay? You know that electrons are particles, but they are also waves, okay? So the same way, if you have a conductor that has defect, and you have always defect in a metallic structure, okay, electron that will propagate through the system will be scattered also by this defect. And his claim is that in one dimension, you always have some disorder and you cannot have a conductor. The wire will be always an insulator, not a conductor. Why? Because of localization of wave, the fact that wave cannot propagate through the system. I don't go too much into the details, but this was demonstrated in different systems. This is a demonstration with cold atoms. Okay, this is a demonstration in acoustics, in optics, transverse waves. In microwave, I'm going to show you how it works in the microwave regime. So this is the experiment that we did some time ago in Nice. So you see this is actually a plate. Actually, it's a two-dimensional cavity. Okay, so it's like a sandwich like that. We close it. Okay, and inside you have all these small cylinders which are distributed randomly inside the system. So the system is closed and the wave propagates in 2 dimensions inside the system. Okay, and what you can do actually is to measure the field inside. I don't go into the details. And you can show that for particular frequency, for these particular peaks, you remember these sharp peaks that I showed you in transmission, you can actually map the eigenfunction and you see that you have a localized state. The energy is localized within the system inside the scatterers. So that's a very nice illustration experiment. It's very difficult actually to observe that experimentally. That was never demonstrated optically in a 3-dimensional optical system, okay? So this is still a challenge. I mean, more than 70 years later, we are still looking for localization in optics. Some interesting question. Let me just check the arrow. Okay, let me skip that. You will see application immediately. So I want to show you how we can do actually a laser with this type of system. So I will describe to you what is a random laser. And I will show you an example that we developed here in Bar-Ilan. And I will show you how we can control actually this type of laser. So let me go fast on that. So what is a random laser? Let's start by the question, what is a laser? I don't know if you already had a course on lasers. Maybe you started it this semester. The principle of a laser is very simple. You need an optical cavity. Usually you have 2 mirrors, okay? And you need a gain medium. So you have the optical cavity, the 2 mirrors here, okay? And you have in the middle, you have a gain medium that will amplify light. So light will be trapped for some time between the 2 mirrors and will go back and forth and will be amplified within the gain medium, okay? And you know that the particularity of a laser is that there is a threshold. If the gain can compensate for the losses of the cavity, then you have lasing. That's the criterion for lasing. Gain should be larger than losses. Okay, so losses for the cavity from the outside and gain inside the system, and that gives you lasing. So that's a very rapid definition of a laser. What happens if you don't have mirrors, but instead you consider a scattering medium like that? You see, so you consider particles, scatterers, okay, that will scatter light. Okay, and you can imagine that they will act as the same way as mirrors. They will force the light to stay a long time inside the gain volume. So we have a gain volume here in blue. Okay, is the gain volume, and the multiple scattering of light will force the light to stay there and to be amplified. Okay, so you can imagine if you take a gain medium which is large enough, okay, there will be a critical volume for which the gain, which is in volume, will compensate exactly for the losses which are only on the surface of this sphere. Okay, so you can imagine that gain can be larger than losses in this system for a critical volume. So you can expect to have lasing in such a system. And that was demonstrated in 1999. You see here that was a sample made of powder of nanoparticles, zinc oxide nanoparticles. They actually provide for gain because they are active actually, but they are also scattering. Okay, and what was shown, you see here, is that when you pump the system, so you have to pump to excite the particle in to pump the system to have the particle in their excited state. Okay, you see that after a certain threshold, you have enough gain to have lasing, which is seen here by these very sharp peaks. That means that you have light emitted by the system at these particular frequencies here. So at low pumping energy, at higher pumping energy where you are in the multimode regime. So lasing in the scattering medium without mirrors is possible. So we can have a laser without mirror, a kind of mirrorless laser, which can be very useful, for instance, in the domain of the UV or the X-ray, where it's very difficult to manufacture mirrors. Actually, it is impossible to have perfect mirrors. Here you have a concept that can realize a laser at those frequencies. Okay, so there have been many studies on random lasers since then. I just skip that, and I will show you now what we have done here. So we designed this particular structure here. So it's a polymer. So it's kind of plastic, a plastic waveguide. Okay, PMMA is just a polymer. Where is my here? So you see the structure. So that's like a kind of plastic waveguide, which is doped with a dye laser, the DCM. So this is the gain medium. And how do we introduce scattering? Actually, we just carve grooves. You see these grooves inside the system. Okay, so the light will propagate in that direction. Okay, and will be multiply scattered by these different grooves, by these different lasers. You can different layers. Sorry. So you can see here in this microscopic image. You can see there is a zoom here. You can see it more clearly. So that's the polymer structure which is doped. So the gain medium is here, and that's just an air groove, okay, which acts as a scatterer, okay. So in the system, you see that you can have many grooves, and you can have multiple scattering. It's a one-dimensional system, okay. And we can force light to be actually localized in that system, okay. So that's a view of the experiment. So you need to pump the system to excite the dye molecules. You have to pump it. So that's the green. Actually you have a big laser, which is used as a pump to pump the system from below. And you see the yellow light here is the emission of the random laser. So when you pump the system from the top, so there is actually the green light just shine on the top of the system. You see in the plane emission, okay, and you see what happened here. As you increase the energy of the pump, as you increase the gain, at the beginning nothing, at some point there is there is a turn on of the laser, onset of the laser emission, which goes very rapidly after that. And you can see from the top, you see the grooves. Before lasing, you don't see anything. On the top, just fluorescence from the dye. And when you have lasing, you can see from the top the light that can escape through these small grooves. So that's the regime, multimode regime of lasing. So you can make a very simple laser based on multiple scattering of light, okay, without mirrors in this system. The question is that, okay, that's very nice. Okay, we have a very simple way to design a laser. The question is, can we control the emission of this laser? You see that if you look at the spectrum here, the wavelength are completely unpredictable. Okay, they depend on the disorder, on the arrangement of the scatterers. Okay, on the disorder, and you cannot say where you will have lasing. So if you want to make a blue laser and it's going to be red, that's not good. Okay, you want to have some degree of control, and that's what we explore in our lab. How can we actively control a random laser? So the idea is very simple and is the following. Sorry. So the idea is that, so you recognize here the 1D structure with the grooves, okay? The emission of the laser in the plane and the pump. From the top, you pump with the green, okay? So the idea is that can we control the spatial profile of the pump to control the emission of the laser? If instead of pumping uniformly my laser, I modulate, I shape the intensity profile of my pump, okay, can I actually have some degree of control of the system? And that makes sense, yes, because you understand that if I pump my laser in this area here, I will have a different emission spectrum than in this other area here. Why? Because it's a different disordered system, so it will emit differently at different wavelength. So if I can control this modulation, I can actually control the emission of the laser. So the idea is to start with a uniform pump, then you get a multimode laser. And the idea is by using a feedback loop here, we want to select one particular peak in the spectrum and remove all the others by modulating the pump, the profile of the intensity of the pump that excites the system. So that's the setup. I will skip that. To modulate the light, we use what is called a spatial light modulator, which is actually exactly what is used to project my screen on my computer image on the screen. Okay, so those are pixel, liquid crystal pixel that actually can turn from transparent to completely reflective. Okay, and that is used to control the pump profiles. So here is the experiment. So I start from a uniform pump of my laser, and I have a multimode spectrum. And I want to select, for instance, this particular peak here at 561.77 nanometer, okay? So we iterate the system. The system will try to find a different configuration, look at the spectrum until it will optimize the spectrum to select this peak and kill all the other peaks. And that's what you get after a few hundreds of iteration. A beautiful single mode spectrum. So you have a laser which is controlled at a particular frequency of emission. I show you the live experiment here. So here you will see the spectrum. So just to well understand this movie. So that's the spectrum, okay? And that's here on the top here, you have the intensity profile of the pump, okay? So we will try different intensity profile. And for each intensity profile of the pump, we will get a different spectrum here. And the idea is to select the green mode and to kill all other. The red triangle here shows the mode, the highest mode, which we don't want, that we want to eliminate, okay? So this is almost a live experiment. So So you see different configuration of the pump here result in different spectra, emission spectra of the laser. Sometimes the green is higher, sometimes it is lower than the red. And the system, using some optimization algorithm, the system is looking for the best profile to select the green against all the other modes. And here you see we catch some good profile. The system catch some good profile and try to optimize it now to reduce the intensity of all other modes. Okay, so that's how we actually can control the emission of the random laser. So that's a breakthrough in the field to be able to control something which is completely random a priori. We are able to control it. I skip the detail because we don't have too much time. And what is very nice in this system actually is that we can select one mode and we can look at the profile of this mode inside the laser. And we discovered actually that those modes are spatially localized. So that's what you obtain when you, that's the spectrum, the emission spectrum of the laser. Sorry, that's the spatial profile that you obtain when you pump uniformly the laser. But when you select each frequency of emission of your laser, that's what you obtain. You see for different wavelengths, you see along the sample, you see that the energy is localized here on this side, here, there with different extension. All those profiles are different mode, localized mode within the system. So we have here a direct demonstration of Anderson localization in one-dimensional system. Okay, so that's the conclusion. So we are able to operate a random laser in a single mode operation, spectral selectivity, and we can actually observe localized lasing mode in this system. So that was published in Nature Physics. You see the title here, the random laser tame. Okay, we can actually tame it, we can control it. Many perspectives around that. We want to control other characteristics of random laser. We want to control other class of laser. Actually, there have been many work after this work where people are using this technique to control different class of lasers. Controlling not only the emission spectrum, but controlling also the directivity of the laser. And okay, so that will be the goal, to have something which is fully controlled. So you see, you have actually a device. And instead of changing your laser, okay, I have green, I want blue now, okay? So you say, okay, I change my laser. But here you just change the pattern of your pump and you switch from one color to the other color, or you switch from one direction of emission to another direction of emission. Okay, so that's a very versatile laser and a cheap way actually to realize this. So that would be like an application, an interesting application of that. Okay, I skip all that. And I have maybe 15 minutes more, yes? That's it, yeah? How much?
25.
25, wow, okay. I thought I had to finish around 6, so that's good to get. So let me take some more time to describe another class of system, which is also one of the main fields that we are exploring in the lab. So this is the field of metamaterials. So when you say meta, usually you mean something, that's a very famous word these days, but that's very old in physics. Meta is between micro and macro, okay? Micro structure means very small structures compared to the wavelength. Macro means very large compared to the wavelength. And meta is in the middle, okay? Is where the wavelength is still comparable to the object and the size of the system, okay? So what do we want to do here? The idea here is to design artificial materials with novel properties, novel functionalities, things that you would not find in nature. So what do you have in nature? Usually you have materials made of atoms or molecules, okay? And usually the field that will interact with this medium is much larger than the microscopic structure of the system. So what you explore is some macro properties of your system that will interact with light, okay? So the idea is, can we replace these atoms? Actually, we are quite limited in terms of atoms, you know, these big tables. And we like actually to design some fancy type of atoms. For instance, some nice resonator that you will not find in nature that will give us new properties in the system. Okay, so the idea actually is to engineer the structure, the medium through structure rather than chemical composition. Okay, so that's how you will introduce new properties. So here you have one of the first example that was done in the microwave regime, where these small rings here, those are called ring oscillators, replace the atoms. Okay, that's still macroscopic. Okay, because we're working in the gigahertz regime, so centimeter waves. But this is also explored in optics with very small structures like those ones, which are very simple, small resonators. Okay, and because the light, the wave is much larger than the small structure, it will interact with this structure and will actually realize different type of interesting properties. So just to give you a few examples of interesting functionalities that you may want to have. So the first thing that you would like to do maybe, you know what is diffraction? When you have light that goes through from one medium to another medium, the light is bent. Okay, if you look through a glass of water, the light is bent. Okay, so we'd like to bend the waves in unusual manner. Okay, so instead of the standard Snell-Descartes law, okay, we'd like to have something that go in different direction. We'd like to try to change that. So this can be done if you can imagine some negative refractive index. So you know that the refractive index is usually 1 or larger than 1. Why not something less than 1 or even negative? Okay, so if you keep the same law, the same Snell-Descartes law, okay, but so the n, so you have n1 sinus I1 equal n2 sinus I2. Imagine that one of the n is negative. Okay, so that means actually you flip the angle. Okay, so that will be quite interesting. One of the goal behind that would be cloaking. You know what is cloaking? You want to hide an object or hide someone from to make him or it invisible to light or to any type of wave. Designing new type of lenses like flat lens. You have a flat lens, something extremely narrow that will replace these horrible lenses. Okay, something more fancy, more nicey. Also some challenge, you know, that when you want to do microscopy, you are always limited by what is called the diffraction limit. You cannot go beyond typically half a wavelength, okay? So that's why usually when we want to do very precise imaging, we use very small wavelength, okay? But we are always limited by this diffraction limit. And the idea, can we design a material, a kind of new type of lens that can achieve super focusing? Okay, you want to go beyond this limit and be able to see, to image very, very small objects. This is very important, for instance, in medical imaging. If you want to detect a tumor before it starts to be too large, before it starts to be dangerous, okay, and active. You want to image detail in the body, all type of challenges that are nowadays problem in medical imaging. So that would be extremely useful to be able to achieve super focusing. So I'm going to show you an example of negative refraction. So, okay, so let's think 1 minute about what will be negative index of refraction. So you have this beautiful cartoon from the New York Times. Okay, so you see what you expect here for a positive and larger than 1 index of refraction. So when you look at your glass of water, you see how the straw is broken. Okay, there is a shift here, there is an angle. Okay, and you can calculate that with the Snell-Descartes law. If it's 1, okay, so you have a matching of the index. So you see the straw is straight. And they tried in this picture to imagine what would mean a negative index of refraction. Okay, so I mean, I let that to your imagination if this is correct or not correct. But that's a kind of funny picture. There is a simple case. Let's take a system which is +1 outside the lens and -1 inside the lens. Okay, so that's the example here. This is called the Veselago lens, and that was proposed theoretically. So you have a source here. Okay, you emit light. And when the light will meet the medium with negative index of refraction -1, it will just reverse direction here. We just apply the Snell laws. It will reverse direction. And when it will escape from the medium, it will reverse again. Okay. So you see with this simple slab, okay, flat lens with the index of refraction -1, you can achieve focusing from one side to the other side of the lens. Okay, so a very simple concept to achieve a flat lens, a focusing flat lens. And actually it was proposed and demonstrated theoretically by John Pendry that this type of lens can achieve super focusing. Actually, when you focus on the other side here, you expect to have a focal point which is smaller than the diffraction limit, than λ/2. Okay, and I want to show you that we did a nice experiment in acoustics. Which is the following, which I'm going to describe to you. Okay, so we want to reproduce this experiment. We want to have a lens which is flat. Okay, we have a source on one side, and we want to refocus on the other side of the system. And the system that we consider is here. So it's a plate. Imagine a thin plate, 0.5 millimeter thick, I think, or maybe 1 millimeter. It's not written, whatever. Okay, so this plate, if you excite it with a piezoelectric device, you will have vibration. Okay, so we are interested at what we call flexural waves. So we vibrate the system. Okay. And we want to structure it to explore this negative index of refraction. And the structure is very simple, actually, you see here. It's an array, a regular array of holes, okay, that will scatter partly the light and partly we let it go through the system. Okay, so here we don't have disorder, it's a periodic system. But I will show you how this structure can actually achieve the flat lens effect, the refocusing through flat lens. Even more than that, I will show you. So if we work at not at the right frequency, okay, all these, I skip the calculation between all that, how we design the system, but the theory behind that is very interesting. So if we work not at the good frequency, at too low frequency, where am I here? So I show you the experiment. So the structure is at the center, okay, and this is just actually the mapping of the intensity of the. So we have actually a probe, an optical probe that measures the amplitude of the oscillation at every point in the system, so we can map the wave that propagates through the system as a function of time and space. Okay, so here, how it's moving. Okay, so you see the source here that emits these nice wave rings that traverse the system. You see now the holes, okay, and you see that the wavefront diverges away from the source, okay. You see multiple scattering within the system, but nothing happened here. Now will you switch to the frequency where we expect to see the refocusing, which is around 10 kilohertz. So that's a microscopic. I mean, you can come to the lab, you see the experiment is very simple. Everything is microscopic. You can play with that. So again, the source emits here. You see that the wavelength is smaller. We are at higher frequency. The wave travels the system. And after some time, we expect refocalization here. So you see how progressively the energy is focused back at this position. After that, we have multiple reflection on the edges, but we obtain a very nice refocusing at this point. Okay, convinced or not convinced? Yes, it's really amazing that just this very simple system can completely bend the waves back to the focal point. And the magic of it, actually, that's what we discovered in this system, is that as you go over time, okay, as you wait longer and longer in time, this focal point shrinks below the diffraction limit. And you can see, so this is the experiment here, this is the simulation. So if you look here at two different times, early time, 800 microseconds, you see the focal point here. And as you go to later time, you see that the section of the spot here, the focal spot is getting narrower and narrower. You see it very nicely here in the simulation because we don't have the reflection back from the edges. We can actually simulate an infinite system. So you see how the focal point here, the section of the focalization gets narrower and narrower. So actually we can not only focus, but we can also beat the diffraction limit in the system. Not very far, okay, we don't go like lambda over 100, but lambda over 4 or lambda over 5, something like that. So that's a nice illustration of a very simple system, okay, that can actually achieve something quite unexpected. What about clocking? So that's really a dream, you know, that's the dream of these people working this field. So you know this guy, okay, with this clock, okay, Harry Potter, okay, and that's really the goal. Okay, you want to make a beautiful clock like that and just hide behind, and that was so that's the concept here. You want to have, so what does it mean that you have a clock that hides you? It means that if you have a wavefront here that propagates, it should go around a region here where you hide, okay? And at the output here, you should see a flat wavefront, okay? So it's like, so if you see exactly out there what you have at the input, it means that what was in the middle is completely invisible, okay? So how do you do that? And that involves a very nice concept, which is called transformation optics. And the concept is as follows. So let's imagine that you have a Cartesian space like that, okay? Two-dimensional Cartesian space, okay? In this space, light propagates in a straight line, okay? And what you do is that you imagine that you can punch a hole in this system, okay? And then you put your finger and you stretch the hole, okay? You make it larger and larger, okay? So you deform the space. You see that all those lines are deformed, and you create a zone here, which is invisible because the light will go around the hole, okay? So now that's something you cannot do easily, okay? You cannot do that, take the space and do it like that. But what you can do actually is you can do a transformation, you can do a mapping. It's called a conformal mapping, where you transform this space with this deformation back into a Cartesian space, but this time with the variation of the index of refraction. Okay, so you replace the deformation by a a gradient of your index of refraction. Okay, and the light will follow exactly the same trajectory. Okay, because it will be bent by this varying index of refraction. Okay, that's something that you can actually achieve. Okay, sorry for that. I went out of battery. I have to share my screen again. This one. Are you okay on Zoom? You are back. You are back with me. You see the screen? You see it? Okay, good. Okay. So that's the concept of transformation optics, and we are working a lot on this idea. I just want to show you a few examples. So this is not us. This is another group that actually built a clock for elastic waves, as you can see here. So you see the size here compared to the coin. Where is my mouse? Yeah. So this is the clock here, which is a complex structure that will bend the wave. So to avoid the center here. So you see, without the clock, you see how the wavefront is distorted here, diffracted by the hole. And when you put the clock, you see how the wavefront is recovered on the other side of the plate of the system. Okay.
What type of wave? What type of wave?
Oh, that's the same type of wave. It's just flexural waves on this plate here. Okay. So you vibrate this plate, and the vibration. So we have a wavefront which is flat here. The vibration goes through when you put the clock.
It will only work for 200 hertz.
So it's
or other frequencies.
It's band limited, but it's quite a large band here for acoustics. In optics, it's very narrow band. It's very difficult to be invisible for all wavelengths. That's a big challenge. Okay. That's a very interesting example also. Another type of wave, which are seismic waves, okay, which are actually called also relay waves. So you want imagine you have a building, okay, that you want to protect from earthquake, okay. So if you can build a clock around this building, then you can force the earthquake to go around and to destroy the other buildings, okay. So my colleague here from France is here, okay, and he has this project with a French company in building, okay. So what they do is that they make these bores here on the ground, you see. So it's a huge experiment, a huge scale, okay, and they have this source of vibration here. And I try to design this type of system and measure here at the output the effect of the clocking effect of the system. So it's not working yet. They're working on that.
But doesn't them the term with the cloaks, they defeat their own purpose. You can't see what's outside the cloak.
You can see what?
What's outside. The light also doesn't come. Does the light come in?
The guy inside cannot see outside?
Yeah, there's light because the light also doesn't come in. It goes around.
Exactly.
And it defeats the purpose then. What's the point of not being seen if you can see what's outside?
That's true.
It's just a wall,
You have to
basically.
put your head out.
Yeah, it's just a wall. It's the entire purpose.
Right. So here is an example of what we have done in the lab recently, based on this concept of transformation optics. I don't want to detail too much, but the idea here is that you have a structure here. We structure this waveguide so that the wave, so again, those are vibration. So you vibrate your plate, your waveguide here, and you want to follow actually the band part of the waveguide, but you want to stay always with the same vertical wavefront, okay? So actually you can create an anisotropic medium based on this concept of structuring the medium to get a new type of property. So from that, actually you can design a clock. And this is it here. So that's a simulation, and we have done very recently, we did the experiment and it worked very well. So based on the same principle, so you structure these 4 parts here of your plate, with the band going up, down, and here down, up, okay? You launch a plane wave, okay? So you see this diamond here. So if there is no clock, you see how the wavefront is diffracted by this object. If you put the clock, you see actually that you keep more or less the wavefront, the initial wavefront at the output of the system. And I tell you, the experiment works much better than that, better than the simulation. I didn't have time to put the figures in this presentation, but it works very well. That's another interesting application here. The same concept, but it's actually the waveguide, you make it circular, you make an annular thing like that. And what happens is that when the wave propagates through the system, it is rotated at an angle, okay? And then when it comes back, the angle is back to vertical. You can see the simulation here, and you can see the experiment. It was very well. And this can be used for a very, very interesting application. It's called the Mirage Effect. You have the feeling that the object is at an angle because you see some reflection from the object at a given angle. Actually, it's not, just because of this clock that deformed the thing. And just to finish, I show you a last example that we have done also in the group. And this is a very, very simple concept, and that gives you the idea of this mapping. So you take a sphere, okay, and you imagine that you have a source on the sphere, let's say vibration or light propagating on the shell, okay, on the surface of the sphere. If you have a source here, you know that this source will refocus exactly on the other side of the sphere, okay? That's a property of the geodesics. They all meet on the other side, I mean, at the opposite diameter of the sphere. Okay? So any point will refocus on the other side, okay? So we want to use this property to make a flat lens. We want to have a flat lens where you emit on one side, the way we propagate, and we refocus on the other side of the lens, okay? So the idea is very simple. You take the sphere and you make a projection of the sphere. You know that, for instance, for the Earth, when you look on the map, on the flat map, it's a projection of a sphere, okay? There are different types of projections. Okay, this one is called the stereographic projection, where you take a line from the North Pole, okay? And the point here on the plane, okay, corresponds to the point here on the sphere. And on top of the position, you also give an index of refraction, which is related to the ratio of this distance over that distance. Okay, there is some very simple formula that gives you actually not only the position in the plane, but also a landscape of the gradient of the index of refraction. And this is what we realized experimentally in this plate. So this is called the Maxwell Fisheye. Okay, so you don't see very well here, but this is a flat plate. Okay, and then we carve inside the plate actually a profile which is like that with a circular symmetry. So that's the profile here. Okay, and you show actually that this is exactly the projection of the sphere on the plane. Okay, just to explain, in the plate, vibration on the plate, what is the index of refraction is given by the thickness of the plate. So you change the velocity of the wave by changing the thickness. So it's very easy to achieve. And I show you the demonstration here. So that's actually, so that's a measurement, but that's the structure. So imagine it's like a ball like that, okay, very thin. Okay, so we are going to inject light from the top, not light, sorry, that's elastic waves, vibration, and you see how it refocus on the other side of the system. Okay, so that's exactly what happened on the sphere. One point here, refocus on the other side. Here you do the same experiment, but on a flat lens on the plane. Okay, so that's this concept of mapping one system to another system, and there is a lot to do, and we are working on that. I cannot describe everything, but skip all that. And just to tell you that you are very welcome first to visit the lab. And if you are interested in this field, or if you are curious, you can come and work either in summer project or as master student to have can come anyway to have project there, different field, up to PhD student and postdoc student also later on. Okay, that's the requirements to hire you in the group. And with that, I want to thank you for your attention.
Thank you very much.
And I leave here my information if you need that.
Visual fiber optics would be used to serve because not only that it would be